All right, so as we wrap up section 5.3 here, there's just one last little piece I want to talk about, two pieces actually. One is this definition of an accumulation function. It's really something we talked about in our first proof of the fundamental theorem of calculus, the first part. This accumulation function is really what we had defined as that I of x function before. So we're just going to look at that with an example that might be similar to something you could see in your homework. And then I also want to show you how to evaluate definite integrals on your TI84. So we're going to do both of those things here. All right, so first, actually let's go, before we get to that, let me show you, let's go back up to this application problem that we looked at, where the first thing we did is we evaluated this definite integral in part A from 0 to 3. Of that negative 18 times a half to the t power. So I want to show you, there's two places in your graphing calculator where your calculator will evaluate these definite integrals. If you're not really interested in anything graphically, then the first one that we can look at is you're going to find it in the math menu. So you're going to hit math. So my interface that you're going to see at the top, the display, looks slightly different, but the key features in terms of where you find everything and the buttons on the bottom are just like your TI84. So you go into that was the math menu I just went into, and then you want to go down to number 9. So it's that FNINT. So it's like this numerical integration feature. So we're going to go into number 9. Now, the newer versions of the TI84 are going to actually show this integral exactly like we want it to be. So we would start by typing in 0 for that lower limit, and then I'm hitting the right arrow to go up to the upper limit, and then I hit 3, and then I'm right arrowing again to get into the function. So the default here is with respect to x, so we're just going to type it in with an x variable. So we have our negative 18 times 1/2 raised to the little caret, x power. And then we're going to hit enter. And of course, that is exactly what we got, approximately negative 22.7. Some of yours could look slightly different. If after you hit that math number 9, if all you see on yours, I'll just kind of jot this down a little bit off to the side, but then I'll probably erase it. But if all you see pop up, hold on just a second, is the FNINT, if it doesn't look like an integral, then what you have to know to do is to first type in your function. So you would type in, what your function is, and then you would say comma x, you're telling it to integrate with respect to x, comma, and then your lower limits of integration, comma, your upper limit of integration. So if yours gives you this, then that's the sequence, right? So you type in your function, and then your variable, your lower limit, and then your upper limit, separated by commas there. All right, so that's one way that you can use your calculator. Of course, this gives you a decimal approximation. Many times, though, especially if you're working on the homework, maybe through WebAssign, unless they say it around, it wants the exact form. Now, that exact form can look pretty ugly. It can include multiple unsimplified, like many unsimplified radical terms, or it doesn't have to typically be in any particular form, but unless they say to round, they want the exact form. If they say round to a certain number of decimal places, then of course you're good to just use that decimal approximation. All right, so let's wrap up, and then I'm going to show you another way that you can find these values in your calculator as well. All right, so this accumulation function, again, it's really this function that's defined to give you the area under the function from a and then up to any ending value x. And that's really the input variable in this accumulation function, is the final x value for which you want that area under the curve. So it's the accumulation of all of these areas, all of the sum of all of these rectangles, letting that go to infinity. It's the accumulation. Think about this as that infinite summing that we're doing. All right, so first we're just going to write what the accumulation function is. And so in this case, we're just going to have our f of x, so capital F of x is equal to And we're going to have our definite integral here from 0 up to x. And then our f of t is the 1 over 1 plus t squared dt. So this is our accumulation function. Now, if we wanted to actually kind of find what this function is, which is really what we're going to do here, this is now something that we can do with our second part of the fundamental theorem of calculus. Hopefully this is an antiderivative that you recall from section 4.8, I believe it is. So the function that we learned whose derivative was 1 over 1 plus t squared was our tan inverse, or arctan of t. So we've learned that one. And then of course we drop the integral symbol because we've taken that integral, we've taken that antiderivative, but now we have to still evaluate between our limits of integration. So we are going to have our, again, arctan, or if you prefer, tan inverse of x minus the tan inverse of 0. So kind of where is tangent equal to 0? Or you could use your calculator, of course, that's at 0. And so we just end up with tan inverse of x. So our accumulation function here is simply tan inverse, or arctan of x. Okay, let's add a couple other parts to this here. So let's make that, we'll make that our part A, and then let's add on a part B to this. So let's find a couple of values here on this accumulation function. Let's actually find f of 1 and f of the square root of 3. All right, so f of 1, well, we don't need to go through the whole integral because we already have that kind of reduced and simplified down to just the arctan function. So we're simply thinking about, where is tangent equal to 1? And hopefully we know that to be pi over 4. Of course, you could always use your calculator here. So just for fun, if you did your tan inverse of 1, you get 0.78539. And of course, if I wasn't 100% sure if those two are equal, I can just type in my pi over 4. So if a decimal approximation was allowed, it's approximately 0.785, but I would just go with definitely the pi over 4. All right, and then let's also evaluate f of, in this accumulation function, square root of 3. All right, so if I am thinking about where is tangent equal to the square root of 3, you kind of want to think about looking for, so you're thinking about where is tangent, meaning where is sine over cosine of some angle, where is that going to give me the square root of 3? So if we think about our unit circle, if I had square root of 3 over 2 divided by 1/2, that would equal the square root of 3. So I'm thinking about where is sine the square root of 3 and cosine equal to 1/2, and that tells me that this is going to occur at pi over 3. So we could kind of think through it that way. So our result here is going to be pi over 3. Again, I could use my calculator, so I could do my tan inverse of my square root of 3. And then if I wanted to double check my decimal approximation equivalent to my exact answer, of course we see that those two are in fact identical. So 1.047 approximately. So there was another reason I went to that decimal form, because I wanted us to take a look at some graphical interpretations here. So I'm just going to say, interpret these results that we have. We're going to interpret those graphically. All right, so let's start with this f of 1. Now, if I go back to the accumulation function, it was the area under the curve of the 1 over 1 plus t squared function. So if I was to look at, so let's say I was to do, and I'm going to do this on my calculator as well, but if I was to look at the function 1 over 1 plus t squared, so it looks, we'll see in a second, something kind of like this. Okay, so this is my, lowercase f of t, so the 1 over 1 plus t squared function. And so we're really looking at what's happening here, the area under the curve starting at 0, and then going up to some ending value of x. And the first one we're going to look at here is going to be at x equals 1. All right, because at first we did f of 1. So we're going to interpret graphically, and in particular here, I'm interpreting, so for my first part here, I'm interpreting what f of 1 means graphically. So initially, we can think to ourselves, okay, well, kind of based on things that we've talked about as the definite integral being this area under the curve, it was giving us this area right here. That's what we were getting. But then with the accumulation function, what we were just seeing was that capital F was equal to tan inverse of x, or arctan. And so arctan has a graph that looks something roughly like this, and there's some horizontal asymptotes at plus and minus pi over 2, so we have a couple of horizontal asymptotes there. Okay, so this is my capital F function. Okay, I guess I have it written right up above. I don't need to write that again. So that's my arctan that I'm looking at. And so what we're seeing here is that this area that I have highlighted in yellow over there is going to equal the value that we get if we simply sub 1 into this function. So if we sub our 1 into the arctan function, this is the value here. So this value right here, which we determined to be pi over 4, that is equal to this area under the curve of the function 1 over 1 plus x squared, or 1 over 1 plus t squared. Oops, didn't mean for that eraser to be so large there. So let me go back, fill this in. There we go. Okay, so again, this was, sorry, just allow me to fix this a little bit if you would. So this is my value, not drawn to scale here. This is my value at pi over 4. So this value right here, just that output value on the accumulation function, this value is equal to the area under the curve on that original function that's inside of the accumulation integral. All right, so let's look at this, the area under the curve. I want to look at it on the graph. So let's go into y equals, and let's graph this 1 over 1 plus, and I'm just going to default here with the x squared. So 1 over the quantity of my 1 plus x squared. And right now, I don't know if I've done anything, and I'm just going to go zoom, I guess I'll go zoom 7. No, let's do zoom 6, zoom standard. All right, so that's a decent looking graph, but I'm going to kind of change my window a little bit that's more appropriate for what we're looking at here. So let's say I start my x's maybe at -1, and then my y's, or I'm sorry, my x max, let's go out to maybe 2, And then my y min, again, maybe we'll start at -1. Maybe I'll just do -1 to 2 on both of the axes here. All right, so we're really kind of focused in then from -1 to 2. And actually, as I look at my original graph, that I'm going to go real quick back here to my Zoom standard. Yeah, that looked pretty good. I was comparing with my original graph. So again, I'm going to go into my window. Sorry about that. And I'm going to, I liked what I'd had before there. Okay, so I'm going to go from -1 to 2. All right, so as we get back to our graph here, now another way that we can look at finding the value of a definite integral is the way I opened today, which was under math number 9. The other way you can do this, if you're in the graph, if you're really interested in kind of seeing the area, is you can, once you're in the graph, you can hit the second button, and we're going to do a calculation, so it's the second trace. So we're activating that calculate menu. And it is number 7, which you can kind of see your integral notation there. So number 7. And again, visually what you see on mine looks a little different, but your calculator is going to ask you the exact same questions. So you know at the top, if you notice at the top it says left bound question mark. Yours, it may, I don't know if the left bound question is at the top. I think yours might pop up at the bottom of the visual of the graph. But the first thing it asks you for is left bound. And so you're going to enter 0. And then hit enter. And then it's going to say right bound question mark. And so you're looking, in this case, we're going up to 1. So we're going to hit 1 and enter. And then at the bottom, we're going to see that 0.785. First of all, you see the visual of the area, and that 0.785 is, of course, exactly equal to our, up here, we actually did this back on our original work up here in part B. We actually had plugged that in. That was part of the reason I did that. That is the decimal approximation of pi/4. So that's another way to get the value of a definite integral if you really want to see that shading. But otherwise, you can always just go into the math and the number 9 menu. And again, you just enter in, especially if you have a newer version of the TI84, it really just visually looks like exactly what you need to enter. It becomes pretty clear. And so you can also do it that way. All right, so that's how you use your graphing calculator. And then again, this accumulation function is the sum of the area under the curve from some left bound starting point all the way up to x. And that's the variable there. And so when you get done, we can kind of connect a couple of things we've talked about graphically, that area under the curve is actually equal to the endpoints evaluated in the antiderivative function. Those two are equal.